Okay, welcome everyone to lecture six. After we discussed all the linear stuff, and in particular, after we discussed all the stuff about, causal estimation, we go back to a little bit more of classic or structural econometrics. So when we talk about nonlinear models, yeah, so kind of when we have nonlinear models, which actually arise quite frequently in econometrics, yeah, so for instance, whenever you analyze decision-making process of a firm, for instance, yeah, kind of do I want to innovate? Yes. Do I want to innovate? No. That would be a binary variable. If that is your dependent variable, it turns out that this leads to a nonlinear model. However, there can be issues like censored or truncated continuous variables. We will see what that actually means. Well, okay, in short, it means you have a response variable that is only partially observed. Yeah? So kind of part of the variable you can observe as it is, and part of it is truncated. Yeah? So for instance, kind of you don't see in income studies incomes higher than 200,000 euros, for instance. So that would be kind of the censoring. Okay, so we have nonlinear models, they appear all the time. And this is, as I said in the beginning, sort of part of this structural econometrics. Yeah? So we will have to kind of make fairly strong assumptions on a data generating process in order to, do some sensible estimation here. We only do a small subset of models. Nonlinear models is a completely different universe. There's lots of stuff to read there. We will only look at a subset of models. In particular, we look at binary choice models, as I already said, like yes or no variables, right? We first look at these models without any unobserved heterogeneity. And then in the last lecture, we look at random and fixed effects models in the nonlinear framework. And it turns out that this is quite tricky, and this is still a very active field in research. Okay, mostly, but actually always, we will use the maximum likelihood estimator, the MLE. In principle, you can also do other stuff, for instance, GMM, but most popular choice is actually maximum likelihood. Okay, so because I'm not entirely sure that all of you have seen maximum likelihood before, we want to quickly start with a recap of what maximum likelihood does. And well, in short, it simply means that we have a couple of variables, right? So this is kind of the observed data, and we assume a certain density. So we make an assumption. We make an assumption that we know the density of these variables up to a parameter that we need to estimate. For instance, we can say that we assume that all these z variables here are normally distributed. Maybe we can even assume that we know the variance, but theta would be the mean. The mean is unknown, so kind of we're trying to estimate the location of this normal distribution, the center. So here I said that these variables are IID. Well, in principle, we don't need to do this. So as long as you're willing to make whatever modeling assumption on the density, you can allow for dependence, you can allow for non-identical distributions. It just makes the notation more complicated and also the proofs. So kind of we go the easy way, we say everything is nicely IID. Okay, now what is the likelihood? Well, first of all, we take the joint density of all these n variables. That is like this f here. However, because everything is independent, the joint density factorizes. So that's what we see here. And because everything is also identically distributed, you see that there is no I index on the f. So really all the distributions are the same. Okay, so here we have the likelihood. It's just the joint density. So the joint density is the same as the likelihood. It's just that the joint density you think of is a function of the data, whereas like the likelihood is regarded as a function of the parameters. Because we want to like take derivatives of this function with respect to the parameter and so on and so forth. Okay. Now, the maximum likelihood estimator is a very simple idea, actually. Kind of we look at the likelihood, meaning we look at the joint density, and we look at the value of the parameter that maximizes this joint density. So kind of like, given the data that we observe, we simply take the value that makes this observed data the most likely. So it's a maximum likelihood estimate, a very simple idea. Okay, now instead of maximizing this product here, which is computationally difficult and annoying, what people do, okay, so I think I just clicked the wrong button, but anyway, what people do is that they actually maximize the scaled log likelihood. Yeah, so kind of here, we would take the log of the likelihood and scale it by a factor of 1 over n. So that scaling factor doesn't, mostly it's just notation. So it just makes the notation easier for us. And the maximizer of the original likelihood will still be the maximizer of the log likelihood, because like the log is a one-to-one function. It's strictly increasing and therefore one-to-one. And now the product that we had before has now turned into a sum, and this is much easier. So this is like much nicer to deal with, and we don't lose anything by this operation. Okay, now we make sure that we differentiate between the true value of the parameter theta. So kind of this is the value that generated the data, and any other value. So kind of theta naught is the true value. And now the likelihood has certain properties. So for instance, like the true value is going to be the maximizer of the expected likelihood. Now, under certain conditions, the conditions are relatively weak. Okay, so what do we mean here? So let's define the expected likelihood, which is like with this Q notation. This is simply as well as, as the name suggests, the expected likelihood, and expectation means here that we integrate with respect to this density. So we integrate with respect to the true density that has generated the data. Notice also that because everything is nicely IID and we have scaled this thing, so we can just look at a single random variable here. Okay, now in order to show that the true value maximizes the expected likelihood, also notice something. I always write expected likelihood, but more precisely, I should write the expected scaled log likelihood. On the other hand, it's actually it doesn't matter, right? Because the log is a one-to-one function. Now, but in order to show this property, we need an identification condition, and the identification condition is this one here. So kind of when we see that the density at a certain parameter theta 1 is the same as the density with a different parameter, and almost surely means almost everywhere, that, or with probability 1, that means these parameters must be the same. So kind of that's pretty much it. And this is a fairly weak identification condition. So that would it's already strange to think of a situation where this is not happening. Okay, so this is the condition that we need, and then the proof goes like this. So we look at the expected likelihood at any value minus the expected likelihood at the true value. So then we just plug in the definition of this Q, just like, involving the E0 here. And now this involves the log, this involves the log. So we can basically, ignoring any constants, for instance, 1 over n, we can ignore here. Like the difference of two logs is just the log of the the ratio here. So that's just using the properties of the log. Then we use the definition of E0, meaning we just integrate with respect to the true density. And now here's where the magic happens. We have this inequality here. So kind of here the log is on the inside, integration on the outside. And after this inequality, the log is on the outside, integration is on the inside. This inequality is hugely important. So that's Jensen's inequality. And the inequality says that if you take a random variable and you have a concave function of this random variable and you take the expectation on the outside, this is going to be smaller than when you take the expectation on the inside of this concave variable function. This smaller equal sign actually turns around when you have a convex function. So Jensen's inequality is hugely important and it's used in many proofs. Okay, now what do we see in the last step? Well, this in the denominator cancels with this. So what we have is that here we have the integral over f, and f is a density, meaning that this thing integrates to 1. The log of 1 is 0. So overall, we have shown that q evaluated at any theta minus q evaluated at the true theta is less or equal than 0. So kind of that's what we've shown. So this really means that if this identification condition holds, that the true value is really the unique maximizer of the expected likelihood. Okay. Now, why is this important? Well, this is going to be important for the consistency. Yeah? So the consistency intuitively of the maximum likelihood estimator works in the following way. Well, I mean, the MLE maximizes like the observed likelihood, right? So Qn hat is simply the likelihood itself. This Qn hat converges in probability to the expected likelihood, which is maximized by the true value. Yeah, so kind of like this maximizes this, the true value maximizes this, and they both get closer and closer. So you would think that also the arguments get closer and closer to each other. And yeah, this can be made precise. And there's like a famous book by, or actually a handbook of econometrics by Whitney Newey and Daniel McFadden. Daniel McFadden got the Nobel Prize. Whitney Newey is someone that may get it. He's still active. And yeah, so let's look at the proof. We need a little bit more precision here. So again, this is what we have already shown. Then here we assume compactness. Yeah? So kind of the set of all potential values for theta is closed and bounded, compact. We also assume that the expected likelihood is continuous, very weak assumption. And then we have here a condition that is called uniform convergence. So kind of here we see that we don't, without the soup, this would just be convergence and probability, right? But uniformly means that if for any n, I choose kind of like the worst difference, as n goes to infinity, even the worst difference still converges to 0 in probability. Yeah, that's uniform convergence intuitively. And then the MLE is consistent. Okay, now we're going to do something which we have never done in this course before. We actually look at a proof. So just to make sure that we, for once, have seen a proof. And it's going to be a very elegant proof, a very clever proof, but also hopefully not too difficult. Okay, so it's a classic. Yeah, we give ourselves some epsilon, some small number epsilon, bigger than 0 can be whatever. And then from our assumptions, it follows that these three things here hold with probability approaching 1. Yeah, so as n goes to infinity. So first of all, the first thing holds with probability 1. Yeah? So the likelihood is maximized by theta hat. Therefore, it is definitely bigger than the likelihood at any other value minus epsilon third. That's easy. Then here we see that the expected likelihood at theta hat is bigger than the likelihood at theta hat minus some epsilon by uniform convergence. Yeah? So kind of because at any value, Qn hat gets like as close as I want to Qn, I can choose n large enough such that kind of they're closer together than epsilon over 3. So that's kind of the idea here. And again, I do the same thing for the true value here. Okay, so now we have a chain of arguments that simply gives us the following. Q, so the expected likelihood at the MLE, is bigger than the expected likelihood at the true value minus some epsilon. Okay, yeah, no, yeah, let's see what that gains. So what we see already is that the expected likelihood at the MLE is bigger than the expected likelihood at the true value at its actual maximizer. So remember that the true value is the unique maximizer of the expected likelihood minus some epsilon. Can be as small as you like. As n goes to infinity, this thing holds with probability approaching 1. Okay, keep that in mind. Okay, next thing, we're gonna use the compactness here. So first of all, this script n is gonna be like a subset of theta, such that the script n is what we would call a neighborhood of the true value. Yeah, just like think of it as a ball that is kind of around the true value. Now, we say that n is an open ball, which means that kind of like that the surface of this ball is not part of the set n. And because n is open, the complement, whatever is not in n, has to be closed. Okay, now, so that's kind of just like a property of openness and closeness. And theta itself was assumed to be compact, therefore bounded and closed. So if you take the intersection of something compact with something that is closed, and also bounded, of course, well, theta is bounded, n is part of theta, so it's also bounded. So actually n complement is also compact. So here we are taking the intersection of two compact sets. Therefore, we get another compact set. Okay. Now, why is this important? Well, we know that the supremum of any continuous function over a compact set exists. Now, think of like an interval that is compact. Any continuous function attains its sup, or its maximum, if you like so, huh? Over a compact set. Okay, now we look at Q and we look at the sup of this function outside. Okay, wait. There's a complement missing here. That's important. That's important. One second. That cannot be. Cullen, and sorry, I have to put a complement here. Yeah. So we're looking at the expected likelihood outside, yeah, so kind of in this set here. Okay. Is it working? I'm running tech in the background. Yes. Okay, it's working. Good. So this thing is going to have a maximizer, theta star. Can be whatever. Yeah? It's some theta star, but what we know is that Q at this theta star is going to be strictly smaller than Q at the true value, because this is the unique maximizer of the expected likelihood. Okay. And we've already seen that star holds for any epsilon. So now we make a particular choice. We will choose epsilon to be the difference between like Q at its unique maximizer minus Q at theta star, which is like the sup in everything outside a small ball around the true value. Okay, so you just take this, and wherever you see epsilon, you replace this. And what you get is that the probability of Q of theta hat being bigger than Q at theta, like the sup. So what we have here, we are taking the sup over all values, potential values of theta that are outside this tiny ball around the true value. And we see that theta hat is going to be bigger than that with a probability approaching 1 as n goes to infinity. Which really means that theta hat is inside this small ball around the true value. And because if it wasn't the case, if theta hat was outside the ball, that would mean that this would be true. Simply because like this is inside this set, therefore it has to be smaller or equal than the sup over the set. Okay, now basically the proof is done, right? So kind of here we have shown that the functions at these two values get closer and closer as n goes to infinity, but not necessarily yet that the arguments get closer and closer together. And here we have done the final step. Yeah? So we have shown that the MLE is within a small neighborhood of the true value, with probability approaching 1. And this neighborhood we can choose as small as we want. Yeah, we can make it smaller, and this proof still holds, which really means that the MLE has to converge exactly to the true value as n goes to infinity. Cool. Yeah, that was a bit of work, but we're done. We've shown consistency of the MLE under pretty weak assumptions. Okay, some more properties of the likelihood. Now, the likelihood that if you have correctly specified the density, so the likelihood is correctly specified, then it's going to be score unbiased. So what is the score? The score really means we take the first derivative. We take the first derivative, and then we evaluate this thing at a true value, and we take the expectation this is going to be 0. Which is not surprising, because we have already seen that the true value maximizes the expected likelihood. So kind of, this is not really a surprising property. The next thing is that the likelihood is what we call information unbiased. Really, what that means is that you take the expectation of the score times its transpose. So kind of notice here that we take the derivative with respect to theta transpose. This is actually just the variance of the score, because the score is completely unbiased. If we take the variance of the score, which is called the Fisher information, then this coincides with the negative expected Hessian of the likelihood. So the second derivative. Notice that if we have a k-dimensional parameter, both sides are, of course, k times k matrices. Okay, so and the equality here holds component-wise for each of these k times k components. Okay, next thing. Well, plug-in notation, I already explained that. When we write something like this, it means we first take the derivative and then plug in the value that we indicate here. Okay. Why was this whole thing with score unbiasedness and information unbiasedness important? Well, it's important for asymptotic normality. Okay. Again, we have a couple of assumptions. All of them are fairly weak. So, for instance, we need to take two derivatives. They have to be continuous. There has to be some sort of central limit theorem applying to the score, or this is actually the likelihood. So kind of like if we take the derivative of the likelihood, there is some sort of central limit theorem going on, and we need uniform convergence in the Hessian, something that we have seen before. Finally, we need that the inverse of the Hessian of the expected likelihood exists. Okay, good. Under these conditions, we can show that, well, the MLE is asymptotically normal, and important, the asymptotic variance is the inverse of the Fisher information. So I will tell you in a second why this is important. First of all, here again, like just a sketch of the proof. We know that the likelihood is itself maximized at the MLE. Which means that we get the first order condition that if you take the derivative of the likelihood and you evaluate this at the MLE, this will be 0. So what we're going to do is that we simply use a Taylor expansion or a mean value expansion. It's the same thing here. So 0 is this, and now we expand this object here. Theta hat is expanded around the true value. So we get that this is the same as the likelihood evaluated the true value, plus we have to take another derivative, and this thing is now theta bar. So this is something that lies between the true value and the MLE. So this is really just a mean value expansion. So nothing is wrong here. All the derivatives exist. Everything is well defined. Next thing is that we take this part here to the other side. So the left-hand side is 0. So we get, and then we divide by this part, and we want to isolate this part here. After we did that, we also multiply by square root n. So we're doing quite some steps here in one go. And what we get is this thing here. So here we see already what's going to happen. This part, this is asymptotically normal just by assumption. So some CLT works on this part. And this part will converge to the expected likelihood at the true value. Well, why at the true value? Notice that theta bar is in between this thing and this thing. And we know that theta hat gets closer and closer to the true value. So kind of theta bar is squeezed in these two values. And because they go together, theta bar also goes to the true value. Okay. So this thing here, as we say here, goes in probability to the expected Hessian at the true value. Now, we assume that this thing is non-singular, so the inverse exists. So the inverse here will be well defined by the continuous mapping theorem. All good, basically. So kind of by the Slutsky theorem, we can combine something that converges in probability with something that converges in distribution. And in total, we get that this converges to a normal distribution with mean 0. So the mean is 0 because of score unbiasedness. And here we get some sort of variance. And the variance simplifies because of information equality and because of information unbiasedness. Yeah, so we know that the negative Hessian is the same as the Fisher information. Yeah, so kind of this thing here will cancel with F so that there's only one of these things left. And therefore, this whole thing, this whole sandwich formula boils down to be just the inverse Fisher information. Yeah? So this is why the information unbiasedness was important. Now, until this very last step, we have not used information equality or the information unbiasedness. In fact, like the same proof will also hold outside of the likelihood framework. So for general M estimators, M estimators are simply estimators that maximize some sort of objective function, which in our case would just be the log likelihood. What is nice about the maximum likelihood estimator is that it's asymptotically efficient. So this is why this Fisher information business was important. Because like these two super famous statisticians have shown already quite a while ago, that for any asymptotically unbiased estimator, the variance will be bigger or equal to the inverse Fisher information. Yeah? So which means that if the MLE is asymptotically unbiased, which it is, then it's also asymptotically efficient because this is the variance, the asymptotic variance of the MLE. And you cannot do better than that. That's kind of the CR lower bound. Okay, that sounds pretty good. Okay, so let's have a quick break here. We continue with binary choice in a second.